So we've been discussing the equilibrium between evaporation and condensation, and this results in liquids having vapor pressures that are temperature dependent. So if you graph the vapor pressure, and let's just focus on water for right now. This is the purple curve in the graph. If you're looking at its vapor pressure at different temperatures, the vapor pressure is actually fairly low. Remember, this is 1 atmosphere up here. So the vapor pressure of water at 20 degrees Celsius is very, very small, about 20 millimeters of mercury. And then as the temperature increases, the rate at which the vapor pressure increases begins to increase. That is indicated by an increasing slope in the curve. So small temperature changes can actually have big changes in vapor pressure, especially when you're near the boiling point of the liquid. So take a look at ethyl alcohol now, right? When you're well below the boiling point, small changes in temperature have very little effect on the vapor pressure. But again, as you get close to the boiling point, you can jump for about a 10-degree difference from here to here, about here to here to its boiling point. You're getting about a 20% increase in the vapor pressure for a 10-degree temperature change. Here, you're getting almost no, for a 10-degree temperature change, you're getting almost no effect on the vapor pressure. So that was one thing that I wanted to point out. The other thing to point out is that the boiling point of a substance is determined by the temperature at which its vapor pressure equals 1 atmosphere, and I'll talk about this in just a second. But you'll notice that for diethyl ether, it has a very low boiling point, and for water, it has a relatively high boiling point. And then ethylene glycol, this is what we put in radiators, right, has a vapor pressure that's very low, even at 100 degrees Celsius, and it isn't until you get out here somewhere that it begins to boil. So the boiling point of ethylene glycol is actually about 200 degrees Celsius. So on this graph, that would be way out here somewhere. But again, you can kind of see the exponential shape of this curve. It's going up like this and eventually begins to rise up like this, just like the other curves do. So what makes the difference, right? What makes the difference in boiling point between ethylene glycol, water, ethyl alcohol, and diethyl ether? And the answer boils down to intermolecular forces. So boils down to, sorry, I didn't mean that pun, by the way. Ethyl alcohol looks like this in its structure. So it has hydrogen bonding, right? But it also has this nonpolar portion. And then water is the most efficient hydrogen bonding substance because it has, not only does it have 2 pairs of electrons, right? It also has 2 hydrogens to hydrogen bond with. So that's one of the things that gives water its special properties. Diethyl ether looks like this. And while it's a polar compound, some of its polarity is kind of negated by its symmetry. And so as far as intermolecular forces go, it's a relatively weak intermolecular force. Why is ethylene glycol all the way out here, right? Well, ethylene glycol actually looks like this. I'm going to draw it next to its dot for its boiling point. So ethylene is 2 carbons. Glycol means it has 2 OH groups on it. So in addition to being able to hydrogen bond on both ends, right, it also has a higher molecular weight than water. So actually the intermolecular forces in ethylene glycol are higher than those that you would find in water. And so increasing intermolecular force increases the boiling point of a substance. Now this question was actually supposed to be estimate the vapor pressure, because water doesn't boil at 20 degrees Celsius, but estimate the vapor pressure of water at 20 degrees Celsius. So again, that's what I was saying. If you go down here, this was just to get you to observe how low it is down here. That's about 10% of this distance here, so that's why I was saying it's only about 20 millimeters of mercury down here. All right. So what does it mean when a liquid actually boils? Well, as we were talking about, the boiling point of a liquid, the boiling point that we were looking at over here, right? A liquid boils when its vapor pressure reaches 1 atmosphere, and so that's where it crosses these lines. So why is it that the liquid boils at that point? When the liquid vapor pressure is the same as the external pressure, right? Then what can happen is you can form bubbles within the liquid. They can exert a force against the atmospheric pressure and then vaporize within the liquid. So these bubbles that you see in here are from the energy being transmitted from the bottom of the burner here, or bottom of the pot here from the burner, and that extra energy goes to vaporizing the liquid inside this pot. An interesting experiment, if you want to try it, is to actually take like a 2-cup glass measuring cup and stick it in your microwave and heat it until it begins to boil. And what you'll notice is when you're looking at least this is the way it's in my microwave, when you're looking at the measuring cup, so here's your measuring cup, right? And you have liquid in here. The boiling actually happens from the top. And the reason that's happening is because the microwave radiation source, which is heating your water, is up here. And so instead of heating from the bottom, you're heating from the top. You see bubbles actually just forming in the middle of the liquid. Now, once you do this, I'm going to give you a quick word of caution here. Give it a few minutes to cool down, because if you heat this up hot enough, it may get above the boiling point of the water and not actually boil. So if you're trying to do this and it doesn't work, make sure you give it a second, or at least when you go to pull it out, have like a glove on when you pull it out, because every once in a while this liquid will boil when you jostle it, and the bubbles it'll come frothing out of the top. It's kind of exciting, but kind of dangerous too. But yeah, if you put water in a microwave, you'll notice that it doesn't boil from the bottom. It's really unusual to see that, because you're just so used to seeing things like this. Okay. Well, the normal boiling point is when the vapor pressure equals 1 atmosphere. And recently, I think that's been redefined as something that's very close to an atmosphere, so most of us just stick with an atmosphere. It's a unit called a bar. But yeah, the normal boiling point is when the vapor pressure of the liquid reaches 1 atmosphere. So the normal boiling point for diethyl ether is 34.6, ethyl alcohol 78.3, and water is 100 degrees Celsius. And like I said, ethylene glycol is out here around 200 degrees Celsius. I think it's 197 or something like that. Okay, so, but think about this. If you have your liquid, right, at a pressure that's where the atmosphere, at a place where the atmospheric pressure is less than 1 atmosphere, you can get your water to boil at a lower temperature. In other words, here's an example of some data, right? On Mount Everest, the atmospheric pressure is 0.32 atmospheres, and it's 78 degrees at that altitude. If you're on Denali, right, it's 0.46 atmospheres, and the boiling point of the water is around 83. The highest point in the United States is Mount Whitney in California. That's about 0.6 atmospheres, right? The boiling point is 87. So the higher the altitude you go, the lower the boiling point of the liquid, because the atmospheric pressure is lower. So this is a problem for people who go camping and like to cook like pasta or rice. One of the things that happens often is they can't get it to cook properly. And the reason is cooking is dependent on temperature. And when you depend on the boiling of water to cook your food, what you end up with is a mushy mess, because it's actually not cooking. It's just slowly dissolving it at these lower temperatures. Even up in Kings Canyon, when you're above a mile high, about 8,000 feet, you start to have problems when you're cooking food like that. So, as we've mentioned before, vaporization is an endothermic process. And what happens during vaporization is that high energy molecules at the surface get lost during the vaporization process. In effect, it absorbs the energy from the solution and takes it away in the form of kinetic energy. Well, if vaporization is endothermic, condensation turns out to be the opposite process, right? Conservation of energy. So if I have H2O liquid and I turn it into H2O gas, this has a delta H that's positive. Now, it depends slightly on the temperature that you do the vaporizing at. So at its boiling point, it's 40.7 degrees, 40.7 kilojoules per mole. And for the for the vaporization at 25 degrees Celsius, or room temperature, right, near room temperature, it's about 44 kilojoules per mole. So when you're doing calculations with heat of vaporization, it's somewhat important to know whether or not you're doing the calculation for water at its boiling point or water at room temperature. Now, the process for condensation is exactly the opposite. And conservation of energy would tell us then, right, that this process has to be exothermic. So this is heat of vaporization. The heat of condensation is just a negative of the heat of vaporization, or negative 44.0 kJ per mole here. So here are a couple of different heats of vaporization for water, isopropyl alcohol, acetone, and diethyl ether. And these are listed from top to bottom in terms of intermolecular force. Water is the strongest on the list. And diethyl ether has the lowest. So when you're looking at heats of vaporization are also interdependent on also dependent on the intermolecular forces. Maybe not as strongly. These are both hydrogen bonding, right? So the heat of vaporization is similar. Diethyl isopropyl alcohol is got a much higher molecular weight than water. So the heat of vaporization is pretty similar, even though water has stronger hydrogen bonding. And then acetone is polar, and diethyl ether is polar, but not as much as acetone. So you can see there's some dependence on heats of vaporization and the intermolecular forces of the molecule. Another thing, again, that is important to recognize is you'll notice the normal boiling point of the liquid, that is at 1 atmosphere pressure, right? Water is 100, and as you go down in intermolecular force, the boiling points go down. So here are a couple of example calculations, and I'll show you how to deal with signs and things like that. So the first question is, calculate the enthalpy for the condensation of 25 grams of water at its boiling point. The heat of vaporization of water is 44 kilojoules per mole. So this is kind of a common thing, actually, because the way we transfer heat in like water heaters is through boiling water and then condensing the vapor or the steam at different locations. And so we're going to calculate how much heat is released when 25 grams of water is condensed at its boiling point. All right, so to start with, we have 25 grams. And what our plan is to do this. We have grams of water. We're going to have to convert that into moles because the units for this is moles. And then once we have the moles, we can convert that into kilojoules, right, using the heat of vaporization of water. But you got to keep in mind that this is a condensation and this is a vaporization. Okay, so we're going to start with 25 grams. And then we'll use the molar mass of water, which I've calculated is 18.016 grams for every 1 mole. And then 44.0 kilojoules per mole. Now, keep in mind, right, that this has a negative sign on it because it's a condensation, and then we can do that calculation. What you should come up with is something like 61.0, let's see, 568. We'll go back and check our sig figs, right? We only have 3, so we're rounded off to here. So the answer for this one, negative sign, is negative 61.1 kilojoules is the enthalpy for the condensation of the water vapor to liquid, okay? Now, this is exothermic, right? Negative energy, right, implies that this process is exothermic. Now, how much energy is the second part? How many grams of acetone could be vaporized at room temperature with that energy? The heat of vaporization of acetone is 31.0 kilojoules per mole. Right, so a couple of things to keep in mind. Conservation of energy. This is released by the water vapor. But what we're doing is we're going to absorb that energy into the acetone. So the energy for the acetone that's going to be absorbed is just the opposite of this number, because conservation of energy says what's lost by one system is gained by another. So I'll start with the process. I'll have kilojoules of energy from the condensation. Then that's kilograms, sorry, kilojoules. And we're going to convert that into moles, and then we'll convert that into grams. Okay. The way we'll convert it into moles is to use this heat of vaporization of acetone. Okay, so negative 61 point, and I'll use the unrounded number for the calculation, 568. Oops, lost my K there somehow. Kilojoules. And then it's 31.0 kilojoules per mole. And then I calculated the molar mass of acetone. It's 58.08 grams per mole. And then the units will cancel like this, right? I end up with grams. I ended up with 114.39 grams. Again, there's 3 sig figs here. I have 3 sig figs in this number, so that my answer should be rounded to this point here. So I could actually evaporate 114 grams of acetone with the heat from the condensation of 25 grams of water. Okay. So here's a quick concept check. We have 100 mils of water, and we put it into 4 different beakers. And each of the beakers either has a different diameter or a different temperature. So choice A, where we're looking to see which one has the highest vaporization rate. Choice A is at 25 degrees Celsius. It's a 100 mil beaker and has a 5 centimeter diameter. 55 degrees Celsius, 100 mil beaker with a 5 centimeter diameter. And then back to 25, but now this is a 250 mil beaker with a 7 centimeter diameter. And this is a 55 degrees Celsius beaker with 250 mil beaker with a 7 centimeter diameter. So which of these would have the highest vaporization rate, right? Well, we know that vaporization depends on temperature, right? So we know the 55s are higher rates than the 25s. And vaporization also depends on surface area. So if you have a bigger beaker, one with a wider diameter, the layer of liquid will be thinner in the 7 centimeter diameter, but the surface area will be larger, right? So you think about visualizing what this looks like. I have a beaker like this, and it has liquid in it like that, right? And then I have a beaker that's bigger by roughly 40%. I don't know if I can draw 40% accurately, but that's okay, like this. There'll be a thinner layer of liquid, right? But it has a larger surface area. So what we conclude is because the vaporization rate is dependent on higher temperature and the higher surface area, that D has to have the highest rate of vaporization. So to summarize some of the things we've covered in this video, strong intermolecular forces mean that you have low vapor pressures. I should also say when you have low vapor pressure, that means boiling points will be higher, right? Open containers, we have vaporization, which is greater than condensation. Liquid cools as it evaporates. And then when you close the container, the vaporization and condensation rates eventually reach a dynamic equilibrium, which generates our vapor pressure. And then vaporization rate increases with temperature and increasing surface area. And finally, a solution boils when its vapor pressure equals the applied pressure, and that the normal boiling point of a substance is when its vapor pressure is equal to 1 atmosphere. So there's a couple of things that were covered in this video and actually in the last video segment, hopefully summarizing some of the more important points.